Alright, this lecture involves a bit of chemistry, but it's really worth it. So now metabolism is the production of energy by an organism that mediates chemical reactions that capture energy, store it, and use it for cellular processes. Metabolisms either involve oxidation, namely the removal of electrons from a substance that is called the electron donor, or they involve reduction, in which there is an addition of electrons from the electron donor to an electron acceptor. Now, in recent years, we've discovered that there is at least some kind of organism that has evolved to use every reductive, oxidative, inorganic reaction that exists, and of course a whole pile of organic reactions too. This massive diversity of metabolisms makes sense. After all, there is enormous variety of Earth's environment, and therefore lots of ways to make a living by catalyzing reactions. Metabolisms provide power that allow organisms to synthesize proteins, to grow and divide, move, and generally respond to the environment. Notably, even quite energy inefficient metabolisms still exist somewhere, showing they are selectively favored somewhere on the planet. The idea is that an organism sets up a reaction between the donor chemicals and the acceptor chemicals in order to harvest energy from the chemical reaction. The most energy-yielding reactions are those where the donors and the acceptor chemicals are far apart in terms of their electron reduction potential. The bigger the electron reduction potential is between the donors, the reducing agents, and the acceptors, the oxidizing agents, the more power the overall reaction yields to the organism that sets up that reaction. The chain of electron donors and acceptors is called an electron tower. Now, for instance, organisms might use hydrogen, a strong reducing agent at the top of the electron tower, by reacting with oxygen, a strong oxidizer at the bottom of the tower to make water. This reaction involves a big difference in electron reduction potential that yields a lot of energy, some minus 237 kilojoules to the animal. The animal then uses that energy to make ATP that it can reduce later on to give power to run cellular activities. Note for a moment that this reaction that combines hydrogen and oxygen is what blew up the Zeppelin Hindenburg, a giant airship filled with hydrogen over New Jersey in 1937. Now, in contrast, if the oxidizer is not that oxidizing, then the reaction yields less power to the organism that catalyzes the reaction. For instance, the use of hydrogen combined with nitrate yields only minus 163 kilojoules of energy. This is because nitrate is not very oxidizing, certainly by comparison with combining oxygen and hydrogen. Now, when we look at the distribution of metabolisms with depth in sediments, we see something really neat. This is the whole point. The most energy-yielding metabolisms occur in superficial sediments, while less productive metabolisms are usually deeper in the sediment column. Notice that this mostly follows the electron tower described earlier. The most energy-yielding metabolisms are used first because they're strongly selected for. Oxygen is usually abundant in superficial sediments, and it yields very powerful metabolic reactions. We get a whopping 119 kilocalories of energy per mole of sugar made with aerobic respiration. But once oxygen is used up by microbes, the remaining reactions are all anaerobic and produce less metabolic energy for the organisms running those reactions. As it turns out, after oxygen is no longer available, the next most efficient metabolisms are nitrate reduction, yielding 113 kilocalories per mole of sugar. And when the nitrate's gone, we go through manganese reduction, iron reduction, and on to bacterial sulfate reduction. This last yields only 24 kilocalories of power. Then, after the sulfate's gone, metabolic systems like methanogenesis, making methane, still work. But the methanogenesis is terribly inefficient, producing only 22 kilocalories of energy per mole of sugar. So these anaerobic microbes do not destroy organic matter very well. Indeed, once anaerobic metabolisms kick in, because oxygen's all been used up in sediments, the overall rate of destruction of buried remains falls dramatically. Indeed, due to a scarcity of nitrate and manganese, we often jump right to sulfate reduction only a few centimeters into the sediment. And this metabolic reaction is so inefficient that it consumes only a sixth of the organic matter that aerobic respiration does near the sediment surface. Hence, the likelihood of preservation of a fossil increases a lot with just a small amount of burial. This is the key